Hi everyone, welcome to the monthly E3SM BGC webinar. Our speaker today is Jean-Francois Lamarque, the Director of the Climate and Global Dynamics Laboratory at the National Center for Atmospheric Research. And today he's going to talk about chemistry-climate interactions from perturbations of anthropogenic and biomass burning emissions.
Thank you, Kate, and thanks everyone. So I will be presenting some fairly recent and also ongoing work that I'm doing with a variety of collaborators. And so with just a variety of aspects of looking at anthropogenic and biomass burning emissions. I don't know how you want to handle the questions, but feel free to interrupt me if you want. I'm not sure where chats and all that are going to be, so I think raising the question is probably the best way to do it. All right. So the first thing I'd like to talk about is we've been looking at the CMIP6 biomass burning emissions and what they do to the models. And this is an if you baseline the global surface temperature to 1920, 1949, then this is the CMIP6 results in red for CESM2. The equivalent in blue would be for CESM1. We have a large ensemble for CESM1 with 40 ensemble members. For CESM2, we have 11 ensemble members. So slightly different number of ensemble members. And then in black, in black you have some of the reproduction of the historical surface temperature. So overall, you could argue that CESM2 is behaving fairly similarly to CESM over the historical period. We've got the slight stronger dip that caused us a lot of grief as we were putting CESM2 together, but overall, the reproduction of the historical period is fairly similar if we were to do, say, just a bias estimate on this or standard deviation. However, if you want to look a little more carefully, right there, right at the end of the 20th century, beginning of the 21st century, it's pretty clear that CESM2 warms up faster and then either CESM1 or BEST, so the estimate, which is somewhat puzzling, and I think maybe even more puzzling is that right after, say, 2015-ish, and then you start seeing that the CESM2 basically goes back down and starts warming much faster than CESM1, and almost goes back to where CESM1 is. So this was the behavior that got us slightly puzzled. I think at this point we actually do have enough ensemble members, both on the CESM1 or the CESM2 side to identify that this is not just internal variability. And by the way, you can I don't know if you can see my arrow, but there is a slight discontinuity between 2015 because the number of ensemble members for the future is not the same as the number of ensemble members for the historical. So that's little dip there that you can see. So we're looking at this and trying to identify what could be going on basically over this 1995 to 2014 period. And also, just part of this analysis, we started looking much more regionally, and most of the difference is actually over the mid-latitude to polar regions in the northern hemisphere. You can see here delta is much increased over this time period. So then the question is, what could be driving this change in temperature from say CESM1 to CESM2? And this is when we start to look at some parameters and some of the diagnostics, and we'll go to those. But the bottom line is, if you look at biomass burning emissions, and there is a map here of the average over basically this period, for which we have satellite reconstruction from GFED. So here you have an average of the fuel consumption associated with forest fires or biomass burning in general. And if you look at the way the historical biomass burning emissions is that pre-satellite, there is some reconstruction that takes into account as much information as one can find. It could be charcoal records, could be information about land that was burned from historical records. So it's just a mix of things. And then during the satellite, you actually have some ways of accounting for the variability from year to year. This is the biomass burning emissions, I believe for black carbon, for averaged over this period, and this is the annual mean, right? So this is not a reproduction of the seasonal cycle, but it's the interannual variability. And so what we can see is that prior to say the 1990s, the variability into the signal is much lower than what is input into the model. And so we started to look at this, and in CMIP5, the biomass burning emissions over this period were just using the average. We didn't try to use this interannual variability. And so we basically had something that is this green line. And so we decided, okay, let's just use those emissions into the CESM2 CMIP6. So have the same historical, and then starting in 97, we have basically a flat line, but the overall integrated amount is exactly the same as the interannual variability, and we keep having the seasonal cycle. It's just a mean seasonal cycle of those emissions. And so what happens is, if you focus over this time period here now, 1992 to 2020, just by changing the biomass burning emissions of our aerosol precursors, but mostly it is, in this case, black carbon, what you end up is, both on the global and on the polar region, global surface temperature, you can see that just by removing this variability, you can actually reproduce the variability that we see and the trend that we're seeing from the CMIP5 version, and so also much closer to the observations. So just by turning off the variability of the fires from year to year, we're able to basically recover the temperature that we're seeing. So we're looking at changes globally of 0.2, 0.3 Kelvin, which are actually fairly critical in some of the estimates of, for example, climate sensitivity based on the historical record. So this is really critical in understanding, on using historical reconstruction and historical simulations to understand the behavior of the model. So why is this happening? So we're still looking into the details of it, but if we try to understand, so this is a fairly complicated response. It's a difference of a difference. So the difference between the later part of the 20th century and the 20 years prior to that. So we can compare how changing the emissions compared to the original CESM2 CMIP6 version changes, right? So changing to the new biomass burning emission means that over that period, the warming, and which is very much concentrated in the polar regions, has decreased very, very significantly. So this is exactly what we were seeing before. And this is very much a cloud aerosol interaction. So cloud droplet and short wave, the cloud droplet is strongly increasing. So what we were seeing before was basically a very strong reduction of the cloud droplet number, and as that would impact the low cloud amount. And this is what is the response, including some larger scale response, maybe having some PDO pattern attached to it. So there is a large scale global response, although for the most part it's concentrated to the mid latitude to higher latitudes. And so we can obviously look at the shorewave cloud forcing associated with that. So it's that balance of changing the emissions and pumping, probably in a very, very nonlinear fashion, very large amounts of biomass burning aerosols versus keeping it much smoother. So this would be interesting if it were CESM2, but what it becomes really interesting is that seems to be much more a CMIP6 wide impact. And in particular, so CESM2 is right here. So it's on the high end. So this is the change as in the shorewave cloud forcing downward over the 40 to 70 north. We're looking at basically the transition from the standard biomass burning to this much higher variable biomass burning. And so you have here the list of the models and the mean change over this period, and this uses a 4-year running average, kind of smooth down the signal. The multi-model mean is here. So what we're seeing is that on average, the CMIP6 models are seeing a significant change in the shorewave cloud forcing, in the shorewave downward, as we are seeing in CESM2, although CESM2 is probably more sensitive, just about twice as sensitive as the multi-model mean. But this is still something that then is indicating that the vast majority of the models are responding in a similar fashion to what CESM is showing into this. So we've actually started to look at trying to entrain some of those models to try to see if they're seeing a very significant or very similar response to the biomass burning emissions as what we are seeing here. So, but we don't have those results yet. This is work that is under review right now. One thing that you could expect, obviously, is that this would have also an impact on sea ice. And so we're doing the same experiment here. Again, there was some very significant trends, so both in the surface temperature, as I've shown before, but how this would impact in the overall sea ice here in the black line. And so removing the variability in the emissions is actually now something that we can trace back to being just a variability in the biomass burning emissions. And there's a variety of aspect to that, one being the albedo, the actual temperature, the forcing. So it's not very clear that it's not just a black carbon putting on sea ice. No, there is a variety of factor, but clearly there is a signal that can be identified from biomass burning into the sea ice. And so we also have this shape where there was that apparent recovery here. And again, that's because you go from highly variable back to into the future, and all the SSPs or the RCPs in CMIP5 have now, again, a very smooth varying climatology into the future. So there is all this. So I think this has been really interesting and puzzling at the same time, right? So what we have found is a really strong signature of biomass burning in the Arctic, and this is related just to the emissions from biomass burning into the region poleward of 40 degrees. We only changed the biomass burning over that region. And of course, that variability is observed, right? So the problem is not so much that the variability is occurring. It's that somehow, I believe, the way we have tuned the model, or the way we understand the model and the model behavior, is usually based on pre-industrial conditions for which we do not have variability. So what this is bringing into light is that the way we've been doing whether reconstruction of biomass burning for the historical period, for the pre-industrial, or putting into the future is just inconsistent with the biomass burning that is actually observed. And it's that inconsistency that is showing up into this behavior that we're seeing late 20th, early 21st century. So I think somehow this is now putting into focus the need to look at the variability of biomass burning emissions much more strongly. And I think this means that going forward, we really have to look at reconstructing, or maybe using, maybe this is really now the place for using interactive biomass burning emissions, and how those should be used and considered for all simulations, whether they're pre-industrial, historical, and future, because otherwise, or we go back to the CMIP5 protocol of a very smooth, slowly varying signal. But if we want to capture what is actually happening in the real world, then we have to make sure that it happens also in the past and into the future. So this is the first part of my talk, and I'll switch gear now and start going and start looking at anthropogenic emissions, so that I cover everything that was in my very vague title. And I'm sorry, I don't know who is on the call, so hopefully not too many people will be offended by giving a very short introduction on sulfur chemistry, which is very, very short. So the bottom line is sulfur chemistry is strongly, the main sources are sulfur dioxide, that comes from mostly volcanoes, whether they're strongly erupting or the type that's sputtering. Almost what is considered in most models as being constant over time. Power plants, and also more on the natural and possibly with some biogeochemical feedback, DMS, creating, being oxidized in the atmosphere and creating SO2. From SO2, we form sulfate through a variety of oxidants, whether they're in gas phase or aqueous phase. You end up with particles, sulfate particles, which again then be transported, and then with deposition through either just dry deposition or wet deposition, And the overall global lifetime of sulfate is about 3-4 days overall. So, and it would be a lot stronger if this is an SO2 emissions into the stratosphere, but their overall tropospheric sulfate lifetime is about 3-4 days. So one thing that I did 10-ish years ago was to start looking at ice cores, because as you can expect, even with a lifetime of 3-4 days, there will be enough sulfate to reach Greenland, for example. And then we can start using ice core measurements over. And in this case, we're just looking at 1850 to 2000 or to present day, of the reconstruction of the deposition flux. So the measurement of ice cores is actually of concentration in the ice, from which knowing the accumulation rate of snow, and don't ask me how they do that, but you can extract, you can do an inversion and get an estimate of the sulfate deposition. And then we can compare it directly with the model, looking at the sum of dry deposition and wet deposition, which could be in Greenland both under the solid phase, snow, ice, or rain, depending on the season. And we're looking only at the annual mean. So this is the red dots were the measurements, annual mean, and then the black line here is what I had for the CAM model at that time. And this is obviously driven very strongly by the change in emissions, and this is the data set created by Steve Smith and collaborators using the CEDS project. And the black dots were the data of the CIMIP5 emissions. These are the anthropogenic SO2 emissions. And for CIMIP6, and there is much more analysis of the interannual variability. And so this is the line, but overall, and they're very, very similar over most of the period. But what we're expecting basically is a very strong rise until the 1970s, when we had the implementation in the US and Europe of the Clean Air Act and scrubbers on power plants. Strong decrease, and then a rebound, at least on the global emissions from China and India, but at this period it was mostly China, and then their own implementation of scrubbers. So really interesting, both long-term and short-term variability in the emissions. So now moving to CIMIP6, and I'm sorry for the quality of the figure. The translation from JPEG to the presentation didn't work so well, but so here this is something I've started to look at, looking at a lot more ice cores, and looking at all models in the CIMIP6 archive. So here I'm highlighted obviously the Wacom 6 model. So the Wacom 6 model has several features. It's a 1 degree, has very extensive chemistry, both tropospheric, stratospheric. It goes from the surface to 150 kilometers. And so I have a full representation of stratospheric chemistry. This one is also driven by volcanic emissions. So the emissions of large volcanoes and smaller volcanoes, but all the eruptive volcanoes is actually specified as an input to the model in terms of SO2 emissions, from which there are now part of the MAM4 in this case, model. So we have a representation of the formation of sulfate from SO2 in the stratosphere, and then going through the whole cycle of transport and then deposition. So here, a slightly different representation than the previous slide, but the data are still in red, but as a line. The model here is in black with the blue shade, which I'm hoping you can see well enough, is the 1 sigma, and it's only 3 ensemble members for this analysis. So a few key points here. Overall, and this is for the Greenland D4 site, which is the same as the one I was showing before. So we can see some of the high peaks from the models. This. Those are all volcanoes. We can go back to the reconstruction that was performed. We're actually finding both some of the high variability and the long-term trend from the observations being very well captured by the model. Interestingly, in the the late 20th century, beginning of the 20th century, we don't seem to actually do so well. So it's unclear at this point, and this is ongoing analysis that I'm doing, and it's unclear whether there is just that we get the overall trend here from the changing the anthropogenic emissions to be fairly well captured, maybe slightly slower than observed, and it would have then maybe a constant bias in the emissions, maybe volcanoes or from DMS over this time period. And they would indicate they would create this shift. So one thing that I can do is to use the multi-model mean. There are about 15 different models that for in the CMIP6 archive of the historical emissions that have provided the sulfate deposition fields. And so interestingly here, the multi-model mean, the black line, and standard deviation here, which is over much more than 3 ensemble members, I think it's over probably about 100 different simulations in here, is actually very similar to what I'm seeing in the Wacom results, which, well, a lot of the CMIP6 models do not put the volcanic emissions as SO2 emissions, so they would not be captured in this. So I think what this is indicating is that right now, either there is something incorrect in the way the emissions are being implemented or input into the model, or that there is something that none of the models are capturing, maybe a shift in transport pattern into the Arctic, or a change in the DMS emissions. But again, different models are doing DMS very differently. So I'm expecting that because the multi-model mean is still much higher, there is something specific on the anthropogenic emissions. As an aside, this is where the multi-model mean, which is the black line here, is beautifully hitting the observations on this side, and it's almost unbelievably so, because some of the models, and I'm not going to name them, even though they're a threat, but they're like factors of too low or too high, and then beautifully and magically the multi-model mean hits everything absolutely perfectly. So it still baffles me how well this works. And then, so compared to what I did in my 2010 paper, I now have access to actually a lot more sites. And so these are now Humboldt and McCall, which is in Alaska. And so I can actually start looking not just at the long distance, but also much more access to not quite local sources, but much more regional sources at least. And we also have access to European and Himalayan ice core records. So I will be putting this together over the next few months, and hopefully they will shed some light, possibly even on emission constraints. All this is bringing me to the next topic, and they're related. And so really trying to identify, to really hammer the point that we will need, that large ensembles are really critical. And this is in our ability to understand standard deviation from the force response from just internal variability. And so this is just the key figure from the BAMS paper from 2015, and this was the CESM1 large ensemble. And just looking here, that basically there on the global scale there is very little variability from one ensemble member to another. There's 30 ensemble members here, but if you start looking at the variability here, something as big as a 23-year surface air temperature trend, 34-year, 34-year, and the linear trend in wintertime surface air temperature, and you can start comparing different ensemble member, the ensemble mean, and see how the regional pattern of those. So it's really trying to understand the variability in those linear patterns of trends and put them into the context on what is accessible for our understanding as a force response versus just internal variability. What I'm going to try to bring this now is into the context of atmospheric composition variability. And there was over the course of a few years, the ATOM and previously also the HIPPO field campaign, where there was a set of transfers flights from pole to pole, going up and down and doing measurements. And ATOM, HIPPO was mostly greenhouse gases. ATOM was much more about reactive chemistry. And so this is some measure. This is from a recent paper that's just submitted, but it doesn't really matter. There's a lot of structures in this. This is production and losses of ozone is reconstructed from the model, but the measurements are going up and down. And so you're capturing a lot of variability, a lot of different signals in there. And so one thing is, how do you place those measurements within the natural variability, the internal variability that you would get? And so we've decided, working with Arlene Fiore from Columbia, to create a Wacom 6 large ensemble. So exactly the same version I have been discussing for the deposition. So this is the full chemistry Wacom 6, 1 degree, fully coupled. That's the version we use for historical and all simulations of CMIP 6. 70 level, about 230 tracers, so it's kind of a beast, but it really gives us a full understanding of the impact of internal variability on chemistry. We want to focus on the 1950 to 2014 period. And so we have 3 ensemble members that were generated as part of the CMIP protocol. And here we're going to try to add about 15 or so members to the existing 3. Those runs are ongoing. And we're using what we call micro and macro initialization, such that we have 3 ensemble members right now from the Wacom CMIP 6 historical runs, and then from each of those 3, we can then do initial perturbation conditions on those. So we will have different both atmosphere and ocean initial states moving forwards. And I will be showing some results of this. But if you remember, my discussion earlier was about that very strong decrease that we see in the 1970s on SO2 in this case, but much more generally on the impact of the Clean Air Act. And so, as part of the ensemble the ensemble for WACM-6, we've decided to create another ensemble, looking at a set of simulations where the Clean Air Act would basically be removed. So what would have been the state of the atmosphere and climate, both on the composition and the climate side, if the Clean Air Act had not acted? And have to admit, so the idea came up to me a few years ago when EPA was being under strong threat, and a lot there was a lot of pushback on some of those policies. So I was trying to maybe see also where would we go back to. And there has been a fair amount of analysis, but they've been not with coupled models. So we haven't looked both at the composition and the climate impacts at the same time. And we know that we should be getting something really interesting. So this is a set of simulations with the previous version of the model, where we were removing the SO2 emissions from over the US, just removing SO2 emissions over there. And we also did China and also in Europe and a variety of regions and all that. But just looking at this, because this would be somewhat similar to the No Clean Air Act. So except that this is we're removing instead of adding sulfur emissions. But we know that this will be the change. This was the change in sulfate that we saw, so very much concentrated over the eastern US, but with the transport over certain distance, change in aerosol optical depth, and the statistical significance attached to it. And then you have a radiator forcing associated with that from both direct and indirect effects associated with the SO2 emission. So, and then we can actually, because we did those analysis through fully coupled models, we know, and we did them with 3 models, CESM, NOAA GFDL, and NASA GIS models. We have a sense that of the impact globally. So we know that it's actually worth doing this experiment because there will be a climate impact attached to it. So we've been working with Steve Smith again, and so we asked him to create a new data set that is consistent with CMIP6, so we can all reuse the CMIP6 simulation, historical simulations, as the counterfactual. And here you have the red is the No Clean Air Act, and the blue is the standard CMIP6. So both for the global and the US, but in this case, the difference is only over the US. So this delta here is the same as the delta there. And so now we have those set of emissions. This is NO emissions. We have carbon monoxide, and just as an aside, these are the biomass burning emissions for those, just for perspective. SO2 and all that. So there will be both tropospheric ozone impact and aerosol impact. So, and just as an aside, just as an example of the type of analysis we have in mind in this. So this is 3 ensemble members looking at the hourly ozone, except that here it's been remapped to daily. As I discovered yesterday, it was almost impossible to see something if you do it hourly. And this is the standard deviation just from the 3 ensemble members. So this is a standard CMIP6 historical simulations that we did with the WACM-6 models. So actually a fairly significant amount of variability, and this is just a single year. Then if you start putting here in red, and I did not put the standard deviation on the ensemble member. We also have 3 No Clean Air Act ensemble members here, but you start seeing this is for 1990. And that you start seeing some differences in the high ozone peaks. But if you remember, 1990 is right here. So the changes are only minor at this point, right? And so you're expecting maybe somewhat of a change in the surface ozone. If you start moving here to the end of that decade, you actually start seeing differences both in the summer maximum that are going to be outside of the internal variability of the system, but also fairly interestingly also some wintertime where the amount of NOx would actually suppress the ozone if you have enough enough NOx emission. This is just one single point in Midwestern US. I just picked one point for the sake of this analysis. So what we have in mind now is to have those simulations, which are and they might be performed. Unfortunately, we screwed up, and so we have to redo them all. So I didn't have as much results as I wanted to. We did. We had a screw up on the SO2 emissions of all places. But these simulations are also being performed by 3SM, GIS, and GFDL and also basing those simulations on the CMIP6 historical simulations that they have. So this will provide not just an ensemble, and then the WACOM 6 will have a large ensemble, probably in the range of 15 to 20 ensemble members, but also a multi-model analysis. And one of the things that we will want to look at are health impacts, because it will be both a PM 2.5 and surface ozone changes, and I showed the ozone changes. Obviously, I will be looking at the nitrogen sulfur deposition and how that would impact, and maybe they will give us an idea of if you change the emissions over the US by a certain amount, and then you will be able to see the impact on the deposition of over ice core, try to get a response function associated with that, but also climate forcing and impacts, and all that data will be distributed. So I hope I can convince people to start looking at those and do more analysis. So just as a partial conclusion for this second part, I think we've been designing and performing what I believe is the first large ensemble for in-depth chemistry analysis. And we're really looking forward to doing analysis and providing the data set to this community. And I think it will provide background information on the observed long-term trends. And there's been a fair amount of discussion on whether deposition, as I'm mentioning, but also ozone sound, surface measurements, and a lot of data that can be used for long-term analysis. But how do we place those into, at the very least, the impact of the internal variability into the system? We expect the ensemble will be large enough to start looking at extreme, especially heat related extremes like surface ozone. Interestingly, Steve is also leading what he ends up calling emissions MIP, which is looking at the impact of changing the emissions. So remember, the ensemble that we're generating is only looking at the impact of meteorology. So in terms of variability and understanding of the full range of uncertainty, looking at the impact of emissions will be important. So I think this is a really nice complement to emissions MIP. And then And then the No Clean Air Act will be put into the broader context of the ensembles to look at the role of regional emissions on climate and composition. And with that, I'd like to thank you for your attention. I'm looking forward to questions.